Hello students, this is Mr. Courtney here. In this video we're talking about atomic theory, and our objectives will be to define an element, discuss how the name and symbol of an element are derived, look at the early developments in atomic theory, describe properties and location of subatomic particles, and we'll also discuss isotopes and use isotopic symbols for an element. Naturally occurring substances are usually a mixture of pure substances. And when we talk about pure substances, we're referring to substances that are made up of one type of substance. And pure substances are either elements or compounds. So they're pure because they're made up of one type of substance. So it could be one type of compound or one type of atoms. And that's what we're showing here. An element is the simplest form of matter that has a unique set of properties and is composed of one type of atom, and they cannot be separated into simpler substances by chemical reactions. Now in this diagram here we have atoms of the same type, so these make up an element. We also have atoms of the same type making up a molecule. But since the atoms are of the same type, even these molecules are considered elements, even though the atoms are chemically combined. So once they're atoms of the same type or of one type, then it's considered an element. Now this is a distinguishing feature between elements and compounds, because compounds can be broken down into simpler substances by chemical means, whereas an element cannot be broken down into simpler substances. So we cannot break it down into other atoms. The simplest form we have here are the atoms of one type of element. So an atom is the smallest particle of an element that retains the properties of that element, whereas a compound is composed of atoms of two or more elements chemically combined in a fixed ratio. So that's why we can break down compounds into simpler substances, but an element cannot be broken down into simpler substances because they're only made up of one type of atoms. Now, how are elements named? There are different features that are used to name elements. One of the things that most widely used, is a word describing a property of that element, and it stems from either Greek, German, or Latin name. For example, gold comes from the word aurum, which means shining down. We have lead from plumbum. Sometimes where the element was discovered, for example, germanium was discovered in Germany. Polonium was discovered in Poland, and californium was discovered in California. They're also named after famous scientists. So like Einsteinium is named after Albert Einstein. Curium is named after Marie Curie. Symbols for elements. Now we use abbreviations to represent elements. The first letter, or sometimes the first two letters of an element in most cases, is either based on the original Latin or Greek name or the current name that is used for the element. Now only the first letter is capitalized. So for example, if we look at boron, only the B, first letter only. We look at chlorine, we lose two letters, not necessarily the first two, but we use two letters from it. And mercury, Hg, which is based on its original name. But notice here, both in mercury and chlorine, only the first letter is capitalized and the second letter is lowercase. With your unaided eye, you cannot see the fundamental particles that make up matter. But early philosophers and scientists were still interested in the fundamental particles of matter. Even though they were not able to observe these particles, they were still able to propose ideas about the structure. Democritus was one of the first to suggest the existence of atoms. He proposed that matter was composed of indivisible and indestructible particles called atoms. But his idea lacked experimental support because his approach was not based on scientific methods, and they did not explain the chemical behavior of elements or of substances known at the time. The real nature of atoms and the connection between observable changes and events at the atomic level were studied by John Dalton, who was an English chemist and school teacher. He used scientific methods to transform the ideas of Democritus into a scientific theory. He studied the ratios in which elements combine in chemical reactions, the experimental observations of Lavoisier and other scientists. His objectives was to determine how properties of individual gases affected the properties of a mixture. The results of his work is known as Dalton's atomic theory, or Dalton's postulates. And his postulates stated that all matter is made up of tiny indivisible particles called atoms. Atoms of the same element are identical but are different from atoms of any other element. So in saying, based on elements we know today, that all carbon atoms are identical, all nitrogen atoms are identical, but they're different from each other. Compounds are formed when atoms of different elements combine in fixed proportions. So there's a fixed ratio in which they combine to form a compound. Chemical reaction involves the rearrangement of atoms, but not a change in the atoms themselves. So the atoms don't change, but they're just rearranged into what substances they were in at the beginning and change to what substances they're in at the end. Now, when we look at the formulas of compounds, there are certain things that we can get from the information given in the formula. So it shows us the types and number, or the ratio of each type of atom in a unit of the compound. So here we see we have carbon and oxygen, so these are the types. And then the subscripts here tell us how many of it we have. Since there's not a subscript here, we know we have one carbon atom. And a subscript of 2 here tells us we have 2 oxygen atoms. So that tells us carbon and oxygen in this compound are combined in the ratio of 1 to 2. All right. The atoms are indicated by the symbol of the element, as we stated, and the number of each type is indicated by the subscript. So again, carbon is 1 because we don't have a subscript. Oxygen is 2 because we have a subscript of 2. In the second compound, we have sodium, carbon, and oxygen in a ratio of 2 to 1 to 3. So let's look at an example. If we were to write the formula for each of the following, and we're going to list the elements in the order that they're given. So if a molecule contains 4 phosphorus atoms and 10 oxygen atoms, how would we write the formula for this compound? Well, we start with writing the first atom given to us, or the first element, phosphorus. And since we have 4 phosphorus atoms, we use a symbol for phosphorus, which is P. And we have 4 atoms, we use a subscript of 4. So that's P4. Then we have oxygen, and we have 10 of them. So oxygen, we use the symbol O. And since we have 10, we use a subscript of 10, P4 or 10. Second one, a compound contains aluminum and chlorine in a ratio of 1 to 3. Similar, but just stated in a different way. So we're not told we have 3 aluminum atoms or 3 chlorine atoms. We're told we have aluminum and chlorine in a ratio of 1 to 3. So that means we have 1 aluminum atom and 3 chlorine atoms present. So aluminum, we don't write the subscript of 1, but chlorine, Cl, we write the subscript of 3. So that leads us now to the law of constant composition. When we think of something being constant, we think of something not changing. When we think of the composition, we think of the makeup. So think of law of constant composition as an unchanging makeup of a substance. If we have any sample of a pure compound, it's going to contain the same elements in the same proportion by mass. So for example, hydrogen and oxygen, always combine in a 2 to 1 ratio to form water. So that's a 2 to 1 ratio, 2 hydrogens to 1 oxygen atom. And the mass ratio is a 1 to 8. When we look at the mass ratio, we get a 1 to 8, 2 to 16, or a 1 to 8. So when we look at it, all molecules of water are going to be in the same ratio. You're going to have a 2-to-1 ratio, and the mass ratio for all molecules of water will be 1:8, hydrogen to oxygen, provided that it's a pure sample of water. So we're going to go into a bit more about atomic structure. We'll look at Thomson's experiment, the Plum Pudding model, MILLIKAN'S experiment, and then we'll also talk about Rutherford's gold foil experiment. We'll talk about J.J. Thomson's experiment. He was an English physicist who performed experiments that involved passing of an electric current through gases at low pressure. The gases were sealed in a glass tube with metal discs called electrodes at both ends. So these are our metal discs here. And these were called our electrodes. This was the positive electrode, and this was our negative electrode. And the gases were inside here in that sealed chamber. The discs were connected to an electric source, and one electrode became positively charged and the other became negatively charged. This resulted in a glowing beam, which he called the cathode ray. So this here is our glowing beam, which he called the cathode ray. And it traveled from the negative end, or the negative disk, to the positive disk. And he noticed that the ray was deflected by the electrically charged plates. And here are our electrically charged plates, negatively charged plate and a positively charged plate. The cathode ray was attracted by the positively charged plate and deflected by the negatively charged plate. As we can see in here, that the cathode ray was bent towards the positively charged plate. Knowing that like charges repel and opposite charges attract, Thomson formulated a hypothesis that the ray was a stream of negatively charged particles moving at high speeds. He called these particles electrons. Thomson went on to set up experiments to measure the ratio of an electron's charge to its mass. He used different gases, different metal electrodes, and still obtained the same results. He found the ratio to be constant and did not depend on the kind of gas used or the type of metal used for the electrodes. So from these results, he concluded that all substances were made up of these tiny particles called electrons, or corpuscles as he called them at that time. And he also calculated the charge to mass ratio of the electron. The discovery of the electron showed that atoms were made up of smaller particles. So that resulted in a change or a modification to Dalton's atomic theory, or Dalton's postulate. And the postulate that changed is that all matter is made up of tiny, indivisible particles called atoms. Since we're finding out here with the discovery of the electron that there were smaller particles than atoms. So these particles were contained within an atom. So atoms were no longer considered to be indivisible particles. Based on his results, Thomson proposed, along with William Thomson, they hypothesized that the negatively charged particles or electrons were evenly distributed in a positively charged spherical cloud. And they call this the Plum Pudding model. It was called the Plum Pudding model because this was a famous food or dish back in England at the time when it was discovered. Robert Millikan, an American physicist, conducted experiments to determine the quantity of an electron's charge. He suspended negatively charged oil droplets between two charged plates. So here we have our charged plates. He introduced oil droplets by using an atomizer to make them very small, and there was a tiny hole at the top plate where these droplets were able to fall through. He used X-rays to charge the oil droplets, and he viewed them through this microscope here. When he varied the voltage on the plates, he observed the effect on the oil droplets' rate of fall. He found that the charge was always a multiple of a certain number, and that number was 1.60 by 10 to the minus 19 coulombs. Using his information, or this charge that he determined, and Thomson's charge to mass ratio, he determined the mass of an electron. And this shows us how he went ahead to determine the mass of an electron. So he took his charge and divided it by Thomson's charge to mass ratio to get the mass of an electron. Ernest Rutherford designed an experiment to test the Plum Pudding model of the atomic structure. And what he did is that he directed a narrow beam of alpha particles at a thin sheet of gold foil. Now, alpha particles are positively charged helium atoms. He expected the alpha particles to pass easily through the foil with little or no deflection because of that positive charge being spread out in the gold atoms. What he observed is that most of the atoms pass through with little or no deflection. So there's no deflection or little deflection. However, a small amount of alpha particles were deflected at large angles. So we have some here at large angles, and a few were directed back towards the source. Based on these results, he proposed a new model or a new theory of the atom. In his new model, he concluded that the atoms are mostly empty space. And his reasoning for this was that there was the lack of deflection of most of the alpha particles. He also said that all the positive charge and most of all the mass were concentrated in a small positively charged region. And this was shown by the large deflection of some alpha particles. He called that region the nucleus, and it is the central core of an atom. So protons were discovered. They were positively charged particles. They have a charge of +1, and they're about 1840 times heavier than the electron. The neutron was later discovered by Chadwick and Rutherford, or some people say it was Chadwick only. Neutrons do not have a charge and have the same mass as a proton. Now, if we look at Rutherford's model of the atom, in Rutherford's model, also known as the nuclear atom, he proposed that the protons and neutrons were located in the positively charged nucleus. So in here, which is the nucleus, we have our protons and neutrons. Electrons are distributed around the nucleus and occupy almost all the volume of the atom. So this is where we'll find our electrons, and they occupy almost all the volume of the atom. Now, if the atom were the size of a football stadium, the nucleus would be about the size of a marble placed at the center. This goes to show how small in comparison to the size of the atom the nucleus is. And that shows us, or demonstrates rather, that most of the atom is empty space. And here we see, if we look at the radius of an atom, or the diameter of an atom, approximately 10 to the negative 8 centimeters, and we look at the diameter of the nucleus, 10 to the negative 13 centimeters. So it's significantly smaller than that. So when we look at the properties of the subatomic particles, it's summarized here. We know the particles, their symbol, their location, their relative charge, and their relative mass. What I want to focus on here is their relative mass, in the sense that in some cases you will see the relative mass of the electron being 1 compared to the mass of the proton, which is about 1836. Some places you see 1800, it's somewhere around that region, or the neutron itself 1839. But if I were to take the mass of the neutron and divide it by the mass of the neutron, we get 1. Divide the mass of the proton by the mass of the neutron, we get approximately 1, and divide the mass of the electron by the mass of the neutron, we get approximately 1840. So that's different ways that you may see. So if you see the electron as being 1, then we know that the proton and neutron has to be in the 1800s. But if the proton and neutrons are represented as 1, then the electron has to be 1 over 1800, 1839, 1840, somewhere around there. Now, so how do atoms of one element differ from atoms of another element? Here we know that they have different numbers of protons, neutrons, and electrons. So atoms of different elements have different numbers of protons, neutrons, and electrons. The subatomic particle involved in chemical reactions would be electrons. So why do different atoms have different chemical properties if they are all composed of the same components? So we have to look at question 1 and question 2 here. It's a combination of them. Because atoms of different elements, they have different numbers of electrons, and as a result, they will exhibit different chemical behavior. Because in question 2, we stated that electrons are responsible for chemical reactions when atoms combine to form molecules. So what is the significance of the protons, neutrons, and electrons in an atom? Here we see that the number of protons in an atom is used to identify the element, and it's called the atomic number. So that is what, when we look on the periodic table, that is what we actually see, the atomic number, the number of protons. Each element is different from another, or atoms of an element are different from another because they have different number of protons. That is what we use to identify the elements. Most atoms, not most, but atoms in their natural states are neutral. That is, they have an equal amount of protons and electrons. So the positive charges and negative charges are equal, resulting in a neutral particle. The mass number is the sum of protons and neutrons. So here we talked about atomic number being the number of protons. An atom is neutral because we have equal amounts of protons and neutrons, protons and electrons, sorry. And the mass number is the sum of protons and neutrons. So when we look on the periodic table, this is what we actually see an element symbolized as. So we have the atomic number, we have the element symbol, so the atomic number is on top of the element symbol. The atomic mass, which we will discuss at a later time, is at the bottom, and sometimes you see the name underneath the atomic mass. So here we have two atoms, and these are two atoms of sodium. There are two things that identify these atoms as sodium. One, the symbol given to us, they're both Na. Two, the number of protons. They both have 11 protons, but this one has 12 neutrons and this one has 13 neutrons. So since mass number is equal to protons plus neutrons, they also have different mass numbers, as shown here. This one has a mass number of 23, this one has a mass number of 24. These atoms are isotopes of sodium. Sodium 23 has 11 protons and 12 neutrons. So this is sodium 23, 11 protons and 12 neutrons. And sodium 24 has 11 protons and 13 neutrons. So isotopes, they're atoms of the same element, but they have different number of protons and neutrons. Or you can say atoms of the same element with different mass number, because when you add the protons and neutrons together, you get a different mass number. So if we look at the nucleus symbol, the nucleus symbol is what we use when we talk about isotopes, or the isotopic symbol. X here represents our element symbol, the A represents the mass number, and the Z represents the atomic number. So just to summarize, mass number is number of protons plus number of neutrons. So that's A is equal to Z plus the number of neutrons. So that means if I want to calculate the number of neutrons in an atom, simply take its mass number and subtract the number of protons, or the atomic number. So mass number minus atomic number, or number of protons, will give us the number of neutrons in an isotope of an element. So the discovery of the isotope, or the neutron, show that all atoms of the same element are not identical, since they can have different number of neutrons, or they can have different mass number. So that led to another change in Dalton's postulate, that all atoms of the same element are identical. Atoms are different from other atoms of an element, but they are not all identical atoms. Atoms of the same element, are not all identical. As we've seen there, they can have different number of neutrons, which results in a different mass number with same number of. Okay, so let's just summarize what we've talked about here. To determine the number of protons, neutrons, and electrons in the atom symbolized above. So we have strontium 90. So the mass number is 90 and the atomic number is 38. If the atomic number is 38, then we know we have 38 protons. To get the neutrons now, we simply subtract the atomic number from the mass number. So that's 90 minus 38, and that gives us 52. And the number of electrons, since it's a neutral atom, would be equal to the number of protons, so that's 38. So we have to write the isotopic symbol for the silicon atom with Z equal 14 and a mass number of 28. We want to know how many electrons and neutrons this atom has. Now be careful here. Because it said Z is equal to 14, don't think that the silicon atom has the symbol Z. Z is our atomic number. So to write that, we know it has a mass number of 28, an atomic number of 14, and the symbol for silicon is Si. So this is what your symbol should look like. Now in terms of electrons, electrons are equal to the number of protons. So the atomic number is the same as the number of protons also. So that is 14. And number of neutrons, we subtract the atomic number from the mass number. So 28 minus 14, and that gives us 14 neutrons. So this takes us to the end of this video. So we talked a bit about the structure of the atom, the early development of the atomic theory, isotopes. We also looked at how elements are named and how they've derived their symbols. So until the next time, I'm out. Blessings.